Hi, my name is Marina, and this is Testing Stochastic AI Models with Hypotheses. Before I dive into the talk, I want to share with you a bit about myself. I live in Tel Aviv, and I've been working as a software engineer for about 10 years, working on different domains both in front-end and back-end, engineering and team leading, enjoying the different challenges. In the last 2 years, I've been working as senior AI software architect at ADOC. In just a few words about ADOC, as it will be relevant at the last section of the talk. In ADOC, we develop advanced healthcare AI-based decision support software. We analyze medical imaging to provide solutions for flagging acute abnormalities across the body. Our aim is to help radiologists prioritize life-threatening cases and expedite patient care. Clearly, the correctness of such programs is just as important as using the best algorithm to find those abnormalities. As a leading company in that field, working with hundreds of hospitals, scalability, reliability, and robustness is a real challenge. My job, together with my team, is to build systems in these standards. In general, over the years, testing has become one of the main focus areas in development teams. A good feature is a well-tested one. In the field of AI, this is many times a real struggle. Since eventually most advanced AI models are stochastic, we can't manually define all their possible edge cases. This led us to explore the best solutions for testing our software. This talk consists of 3 parts. The first part will be mainly theory of testing methodologies in the search for the best approach for machine learning. The second part, I will overview the hypothesis library with code examples. And in the last section, I will try to give you a taste on how we use the theory together with the hypothesis library to test our software. So how do we write tests? The most common and used approach is example-based testing, or normal testing as we like to call them. In example-based testing, each test sets up a single concrete input example and starts to check whether the produced output matches our expectations. We usually aim to think really hard to find those edge cases that will fail the program. And once we do, we fix the problem accordingly and continue adding more examples until we feel that we covered all of the edge cases. I must share that I always felt I'm really bad at that task. And it was really time consuming and never feeling satisfied that I really covered all of the edge cases. And let's do an example to show what I mean. We have a function called merge_sort that merges two lists into a single sorted list without duplicate elements. Here I wrote multiple unit tests, trying to cover edge cases like empty lists, lists with duplicate values, lists with multiple values. It's quite easy to see that there are still many missing edge cases like negative numbers or maybe nulls. And that takes me to the problem of that approach. And it is that it requires us, the developers, to come up with specific examples. We may choose to write 5 or 10 or 100 test cases, but still remain unsure whether we have safely covered most of the edge cases. It's really time consuming, and sometimes thinking about the edge cases is really hard. In addition, in many cases, the requirements of the functions are not defined properly, nor how they should behave for different input types or unexpected inputs. And the interpretation of the developer writing the tests might be ambiguous or unclear, causing missing edge cases and ending up with non-robust tests. At last, we use these concrete examples to suggest a general claim about the system behavior. To be more specific to the merge_sort function, there are multiple unclear questions to the definition of the function. For example, what data types in list should the function support? Are mixed data types a valid input? How the function should behave if it gets null as input? All these unclear questions may lead to missing test cases. Now think about AI software, where the input of the functions in most cases are stochastic and really not easily predictable. How would you think about edge cases there? Let me tell you that. It's probably impossible. That leads me to the next testing methodology, the property-based testing, where many of these issues are mitigated. The property-based tester has to think very carefully about the specification, starting from defining the possible inputs and really analyzing the properties of the behavior of the function, and at last, also the expected output. The idea is that once you have a clear definition of them, you can let the computer do the exhaustive work of generating the random examples and test that the properties are met. To formulate this idea when designing tests, the approach should be as follows. Under what preconditions and constraints should the functionality under test lead to particular post-conditions? Which are the results of a computation and which invariants should never be violated? The combination of preconditions and qualities are expected to be met is called a property. I guess you probably wonder how you come up with these properties. So there is actually quite a small but well-known collection of property-based testing patterns that you can use to start rolling with the idea. And let's look at some examples. One property usually referred as commutativity, and this is when a change of order in applying the function should not change the final result. Here, for example, if you change the order in addition, then the result value wouldn't change. Another property usually referred to as invariant function, and this is when some properties of the code do not change after applying the logic. For example, sorting should not change the size of the collection nor the elements inside. The last example of properties that I'm going to show is the test oracle. And this is when an alternative implementation of the function under test should return the same output. This is achieved by writing maybe simpler implementation, but less optimal, or it's very useful when testing refactor code and you compare the pre-refactor code with the post-refactor code. As mentioned, there are multiple more common properties that can be explored afterwards. But really having these definitions of properties in mind really helps identifying the properties of the function in test. To summarize the purpose of property-based testing, it is to generalize the scenarios by focusing on which features of the scenario are essential and which are allowed to vary. The idea is that once you define the properties, one property-based test runs hundreds of times with different inputs while it really tries to get the test to fail. And it does it by passing all the possible edge cases, empty lists, negative numbers, nulls. Basically, it automates the most time-consuming part of writing tests, coming up with specific examples. To make it more clear, let's go back to the merge sort function. And actually, all the three properties that I showed are relevant for this function. The commutativity, because I can call the function with a different order of the input, and the result will stay the same. The function is invariant in the sense that the elements in the result are all included in the input. And at last, we can probably think of a different implementation, for example, using a different sorting function. The conclusion you should take from this is that we don't always need to know the correct answer, or even be able to check that the answer is correct in order to find bugs, because we can check that the properties are met instead. To complete our research for finding the best methodologies to writing tests for stochastic AI software, we found there is an additional method that helps adding more coverage and completeness of the test. And this is the metamorphic testing. Metamorphic testing was first introduced in 1998 in a technical report, suggesting a new approach for generating test cases. More than 10 years later, it was published in a paper as a valid approach to test machine learning algorithms and became quite common in recent years. This approach addresses the test oracle problem and the test generation problem in machine learning, where in most cases there is no test oracle that can be used to verify the correctness of the computed outputs. If you think about the definition of property-based testing, which I just showed, you should realize that it's actually a property-based testing technique. It gives additional testing possibilities in cases where we don't know how to relate inputs to outputs. And rather than focusing on each individual combination of input and output, metamorphic testing looks at multiple executions of the program. The idea here is to define metamorphic relations which allow us to predict the output after applying a certain transformation on the input. The corresponding test would be if the software reacts to changes in the input as it is expected. And the most important thing about metamorphic testing is understanding what are metamorphic relations. So we basically run the program multiple executions, once on a certain input and the second time on some transformation of that input. We then use metamorphic relations to test if the two outputs meet the defined relation. For example, if you have a search engine for restaurants and you search for restaurants near you, you probably can't predict the answer, but if you add to the search keyword Asian and you search for Asian restaurant near you, you can predict that the answer will be a subset of the previous answer. To give you some examples of metamorphic relations for machine learning, I use the suggested relations formulated in the paper by Xie et al. For classification algorithms. So for example, what you can use is permutation of class labels, addition of classes by relabeling sample, and removal of classes. In follow-up papers, it has been validated that this approach is really effective in machine learning algorithms, and it improves the quality of the software. That summarized the theory I wanted to present and what I think you should know in order to start writing tests for your AI software. That takes me to the second part of my talk, overview of the hypothesis library. Before I dive into explaining the library, I wanted to also mention that property-based testing was actually first introduced by Quick Check framework in Haskell. And there are multiple libraries designed to help writing property-based tests. Hypothesis is such a library, and actually the leading library for Python. You should know that all the core developers are volunteers. They really have great documentation, and from what I have seen, they are really attentive to questions and requests they get. So the key object of hypothesis is a strategy, which is basically the API to describe the recipe for generating data. It's really easy to start play with some simple code testing, and there are many easy to use predefined strategies. The library was written really in a way to do a lot of magic, and it really focuses on finding edge cases. It's also quite easy to write custom strategies. So let's dive into some basics. The main entry point of hypothesis is the given decorator, which takes a function that accepts some arguments and turns it into a normal test function with the generated examples. And in this example, I used the integer strategy, where just as it sounds, generates random integer numbers. Another basic strategy is the floats, where it generates float numbers. And you can see that in this example, the test will actually fail, as floats also generate non-values. And that won't meet the commutative property. So we will fix the recipe for generating data to exclude none, and I actually also excluded infinity, which will also fail the test. And in this way, the test will actually succeed. There are many more basic strategies like booleans, text, dictionaries, and all of them you can see in their specification and how to use them in documentation, and they actually keep extending more strategies all the time. If you need any strategy, search for it in the documentation, as it will probably be there. In addition, there are quite extensive options for NumPy and Pandas strategies if it's relevant for you. Another strategy that I personally find quite useful is the shared strategy that allows two or more shared instances with the same key to share the same value. So basically, it will draw a single value per run. So in this example, I use the shared strategy to make sure that the shape of both arrays are the same. Last, in the core strategies, I would like to show you the data strategy. That isn't really a normal strategy, but instead gives you an object which can be used to draw data interactively from other strategies. I found it useful when there was a strategy that I wanted them to be dependent on the drawn value of one another. So in the previous example, I could have just defined a shape strategy and used data to draw the arrays with that shape. To complete the example from the beginning of the talk, if I were to test the commutativity property of the function, then this is how I would have done it. Generate two random lists with either integers or floats, and start to test the commutativity property. Hypothesis also provides APIs to define your own customized strategy. And let's look at some more examples. The build strategy generating values by drawing from args and KW args and passing them to the callable. The callable can be either a class or a function. Here, for example, we have the rectangle class, and the rectangle list strategy will generate a list that will draw integers for width and height argument and a tuple for the center argument. Then it will pass them to the constructor of rectangle. You should note that if you're using utter library or data class, then you can just use from type strategy to draw class examples. There are also transforming data functions like filtering and mapping that allows additional customizations. You should note though, if your filter is too strict, it may filter all examples or many of them. But don't worry, Hypothesis will tell you that. When you use this kind of libraries that include both randomness and custom building, you want to have debugging tools. And Hypothesis has that. One example is the example function that helps to get the feeling of what the possible values of the strategy, or when you build your own strategy to see if it returns what you expected. There is also the note function that is really like a print function that only prints when the test is failing. There are Hypothesis defaults that can be overridden by using the settings decorator. One of them is a database, which is stored locally in the file system and stores information of bugs when they are found during testing. This information is later used to reproduce the bugs. At last, you can run PyTest with Hypothesis show statistics to get statistics of the run, including how many examples generated, how many were filtered, how many failed, and some more. The random nature of Hypothesis may cause a test to run successfully a couple of times before finding a failing example. Once that happens, it will keep failing with the same example, as it will first retrieve the example from the previous failure stored in the database I just mentioned. This makes Hypothesis repeatable random testing. A bug will never go away by chance. A test will only start passing if the examples that previously failed no longer fails. Hypothesis tries to produce human-readable examples when it finds a failure. It takes a complex example that failed and turns it into a simpler one. For example, if a very long string fails, then it will try to find the shortest failing string. And this process is called shrinking. Each strategy defines an order in which it shrinks, and you can find in the documentation the definition for every strategy. You won't usually need to care about this much, but it can be worth being aware of it, as it can affect what the best way to write your own strategies. So we have the theory, and we have the tools. We are ready to hear about real examples. And that leads me to the last section of the talk, in which I would like to introduce you to some use cases where we found the benefit to use property-based testing together with metamorphic testing using the Hypothesis library. In order for you to be able to understand my examples, let me give you some more context to what our programs do. So as I mentioned in the introduction, we analyze imaging to find abnormalities. And to do that, we train machine learning models that segment the imaging we receive from hospitals to identify those abnormalities. There are many stages to the complete process, and I chose one of them to base my examples for this talk. And that is the extracting features from the segmentation. In this stage, we calculate the features per each connected component in the segmentation. And those features help us to decide whether the relevant segmentation is indeed true or is it false positive. Obviously, I cannot disclose too much of our code, but I wrote some simplified examples to describe the basic concept, which I hope will just be as insightful. So very similar to the example I gave in metamorphic relations, if I have a predicted segmentation with connected components, the extracted features will be included in the list if I add additional connected components to the segmentation. So here I use the composite decorator that also helps generate custom strategies. It does it by calling the draw function to draw random examples and use those values to perform the required modifications. In order to draw random predictions, I use the array strategy that will draw Boolean values in random shapes. Then it will call my custom strategy that will add additional random connected components on top of the given prediction. To make sure it doesn't override the existing components, I use binary dilation to keep them invariant for the change. Finally, I asserted that my returned features list from the first prediction is indeed included in the second one. My second example is a result of really analyzing the process we do, and what I found is that many of the features, like the diameter of the connected component or number of pixels, are invariant to their exact location. And for those features that do change, if I move the connected component, I can mock the relevant functions. So in this example, I wanted to show you an additional way to generate random connected components, and this is by using random shapes function in SciImage. So I'm again generating random predictions, and I assert that the features don't change if I rotate the prediction. And as mentioned, to make the test really succeed, I had to mock the functions that do vary when the exact location of the connected components changes. And that takes me to the end of my talk. To summarize my research to find the best testing methods to stochastic AI models, I came to the conclusion that there isn't one best way. And really the best method is to have a combination of multiple methods depending on the specific process and function we're testing. I hope it did convince you that properly based testing will give great addition to testing coverage, and that I gave you all the information and tools needed to start working on your own testing functions. Thank you for listening to my talk. Goodbye.